In the world of AI, there's this constant battle, this tug of war. On one side, you have amazing quality, that really coherent, human-like text that just blows you away. And on the other side, you've got speed. And for the longest time, it's felt like you had to pick one or the other. Well, today, we're diving into a fascinating new paper that basically asks, hey, what if you didn't have to choose? So, why is this a choice we even have to make? Well, the reason for this really comes down to how the top AI models are built. They pretty much fall into one of two camps, and each has its own huge advantage, but also a pretty big drawback. You can almost think of it like a slow, careful artisan versus a super fast assembly line. The artisan, that's our autoregressive model, is meticulously crafting a sentence, one perfect word at a time. The result is beautiful, high-quality stuff, but man, is it slow. Then you've got the assembly line, the diffusion model. It pumps everything out all at once, super fast, right? But the quality? Well, it's often a bit rough around the edges and needs a lot of cleanup to get right. So let's zoom in on that artisan for a second. These autoregressive models, they're the gold standard for quality right now, and it's all because they work sequentially. They generate the first token, then the second based on the first, the third based on the first two, and on and on. This methodical approach makes sure everything hangs together, but it creates a serious speed problem. Think about it. You literally cannot write the 10th word until you've figured out the first 9. It's a fundamental bottleneck. Now, diffusion models are a whole different beast. They are built from the ground up to take advantage of the parallel power of modern computers. They can spit out all the tokens for a sentence at the exact same time. But here's the catch. Getting that first draft up to that artisan level of quality, that often takes a ton of correction steps, which, starts to eat away at that initial speed advantage. And that's exactly where this new paper comes in. A team of researchers from UCLA, MIT, and Google have come up with something called planned diffusion. And it's this really cool hybrid approach that's designed to shatter that old compromise, to finally get the best of both worlds. I mean, they say it right in the paper itself. Their whole goal is to create a hybrid that combines the strengths of both of these methods. What they're really asking is, how can we get that artisan-level quality, but at the speed of an assembly line? And the core idea behind it all is actually incredibly simple, but also really, really powerful. When you or I write something, not every single part depends on the part right before it, right? What planned diffusion does is it treats writing a sentence like a scheduling problem. It looks at the sentence and figures out, okay, which parts are independent? Which parts can we build at the same time? Okay, so how does this actually work? It's a super clever two-stage process. The model doesn't just jump in and start writing. No. First, it makes a plan. Then, it generates. Let's break down what that means. Okay, so it boils down to these 3 key steps. First, the model kind of uses its slow, careful, artisan mode to think ahead and create a high-level plan. It does this using these special little codes they call control tags. Then, step 2, that plan gets turned into a scaffold. Just think of it like a fill-in-the-blanks puzzle. And then, for the grand finale, the model switches over to its super fast assembly line mode and just fills in all those empty slots at once, in parallel. Let's take a look at a real example from the paper to see what I mean. So say you ask it about the aurora borealis. The first thing it does is generate this plan. It decides it needs 3 separate chunks: a definition that's about 30 tokens long, a description that's also 30 tokens, and a location that's about 10. It's literally mapping out the entire structure of the answer before a single real word is even written. So that plan we just saw, it gets translated into this scaffold. It's basically just a bunch of blank spaces. You've got span A with 30 slots for the definition, span B with 30 for the description, and span C with 10 for the location. And here's the crucial part. Each of these 3 sections can all be filled in completely independently of one another. In this is where the magic happens. In that last step, the diffusion model just fills all 3 of those chunks in at the exact same time. The definition, the description, the location, all generated in parallel. That's the secret sauce. That's where you get this incredible speed up. Instead of needing, 70 sequential steps, one after the other, the model does most of the heavy lifting in just 30 parallel steps. Why 30? Because that's the length of the longest independent chunk. All right, so that's the theory. It sounds great on paper, right? But the real question is, does it actually work? Let's dive into the results from their experiments. And yeah, the headline number is pretty impressive. On a standard benchmark called Alpaca Eval, planned diffusion hit a speedup of up to 1.81 times over the traditional autoregressive method. I mean, that is almost twice as fast. So, okay, why is it so much faster? Well, it all comes back to that idea of sequential steps. If you look at the chart, the old school autoregressive method needed, on average, 367 steps that had to happen one after another. But planned diffusion, because it can do so much in parallel, slashed that critical path down to just 155 steps. That's a huge difference. Now, of course, nothing's free. There's always a trade-off. That super fast 1.81x speedup, it did come with a small hit to quality, about a 5.4% drop. But here's what's cool. The researchers also tested a slightly different version they called dense attention. It's a little slower, clocking in at a 1.27x speedup, but get this, the quality drop was less than 1%. This just goes to show that the whole system is tunable. You can actually choose your own balance between raw speed and pristine quality. And this is what really puts planned diffusion in perspective. When you compare it to other, more advanced diffusion methods out there, it is way, way faster. We're talking 22.4 times faster than one called HDLM. And yeah, sure, a pure, super slow diffusion model might eke out slightly higher quality, but it's 25 times slower. That's insane. So what planned diffusion does is it basically carves out this new sweet spot on the map, offering some of the best combinations of speed and quality that we've seen. So let's pull back for a second. What does all of this actually mean for the future of AI? Why should we care? Is this more than just a cool party trick? Honestly, this next point might be the most important finding in the entire paper. See, as the researchers just kept training these models with more and more data, the standard autoregressive model kind of hit a wall. Its quality just plateaued. But planned diffusion, it just kept improving. Its quality curve kept going up. And what that tells us is that this isn't just a faster method for today, it's likely a fundamentally more scalable and efficient architecture for tomorrow. And on top of all that, it's actually practical. The system has these simple little knobs that developers can actually turn. They can tweak something called a step ratio to trade a little speed for more quality, or adjust a confidence threshold to fine-tune things on the fly. The point is, this isn't some rigid take-it-or-leave-it solution. It's a truly flexible framework. And the author's own conclusion really hammers this home. They don't just see this as one new model. They see it as a whole new framework, a fundamentally different way to think about building large language models that are fast, efficient, and don't compromise on that quality we all expect. And all this leaves us with one big, final question to chew on. For years, the race in AI has felt like it's all been about scale, right? Bigger models, more data, just more. But a technique like planned diffusion points to a totally different path forward. What if the future of AI isn't just about being bigger, but about being fundamentally smarter with its time?